Graph transformations. Another way that we can get new functions from old functions is by putting some mathematical operations onto a function which impacts the way it looks and behaves in a graph. So we're going to look at the different things we can do and what sort of impact it has on our function. So the first transformation that we're going to consider is rotation about the x-axis. That means we're going to have a graph and we're going to mirror it around the x-axis, which is the horizontal axis. The way we do this is by multiplying our function by -1. So for example, if we have the function f of x equals x squared as our original function, then the picture of that will look like a parabola, which is a U shape. By multiplying by -1, we get g of x, which equals -x squared. So that negative is what multiplied our function, and that flips our picture around the x-axis, meaning now it looks like a hill instead of a U. The next thing we can do to a graph is multiplying it by a constant that is between 0 and 1. So that means we're going to be multiplying by some fraction, and the result of that is going to be that it's going to shrink our graph. So consider the function f of x equals sine x. So sine x has a picture that looks like this. So sine lives between 0 and 2 pi. And then it goes all the way up to +1 and all the way down to -1. If we were then to multiply that by -1/2, the result will be a graph that only goes up half as high and looks like this. So notice that my new graph goes to the same zeros. Starts at 0, ends at 2 pi, and travels right through pi just like the original did. But now, the maximum height of my graph is half, and the minimum is going to be -1/2. So what happened was every single y value was cut in half, and it still goes to the zeros because half of 0 is 0. If we were to now multiply our function by a constant that is bigger than 1, the result is going to be what's called vertical stretching. So consider now the function cosine of x. Cosine of x looks like this, comes down, comes up, and it also lives between 0 and 2 pi. It's got a maximum value of 1 and a minimum value of -1. If we were to multiply this function by 4, what that's going to do is it's going to stretch all the y values so it goes up 4 times as high and down 4 times as low. And that will look like this. So again, my graph is going to live between 0 and 2 pi, and it's going to cross through zeros at the same spot. But each y value is going to go up 4 times as high as the original or 4 times as low because we're multiplying every single y value by 4. So again, if we multiply by a negative, it'll rotate our function about the x-axis. If we multiply our function by a number that's between 0 and 1, it will shrink our graph by that factor. And if we multiply by a number that's bigger than 1, it will stretch our graph. There are other things that we can do as well. So let's look at the next batch of transformations. The next types of transformations that we consider are shifts. So we're going to take our graph and we're going to move it around in space. The directions we can move it are up and down or left and right. So we start with a vertical shift. The vertical shift is going to happen when we add or subtract a constant from our function. If we add a constant, that's going to move our graph up. If we subtract a constant, that's going to move our graph down. So here, k is a constant. So consider the function e to the x. E to the x is exponential, and it crosses through at x equals 0, y equals 1. So here, if we were to take this function and we were to add 2, e to the x plus 2, what that would do is it would shift our function up by 2 units. So e to the x plus 2 is the same function shifted up 2 units. If we were to consider what would happen if we subtracted 1, it would take our function and it would shift it down 1 unit. So then we would have e to the x minus 1. So instead of crossing through at 1, it would cross through at 0 because that whole point was moved down 1 unit as well as all of the other points. So this is somewhat intuitive, that if you add a number to your function, it'll get shifted up that many units. And if you subtract a number from your function, it'll get shifted down that many units. The horizontal shift, however, is not as intuitive. Instead, it's a bit counterintuitive. So consider the function x cubed. The function x cubed looks like this. And it turns out that if you were to subtract a number from inside the argument, so notice here we are now inside the argument. If you were to subtract a number in there, that's going to move it right k units. So subtraction moves your function right. Now to me that's counterintuitive because if I subtract something, I really want to move it to the left, but that's not the case here. And if you were to add a number inside the argument, that's actually going to shift it left k units. So going back to our x cubed, if we have x minus 4 cubed, that's inside the argument. And since subtraction, it's going to move right 4 units. 1, 2, 3, 4. So now it's going to have the same shape, but it's going to cross through at x equals 4. Now, if you were to plug a 4 into that function, you would get 4 minus 4 cubed, which is 0. And that's what we want. When x equals 4, y should equal 0 because that's where we cross to the axis. Similarly, if we consider x plus 1, that means we're shifting left 1 unit. So here we're going to come down and we're going to go through at negative 1. So again, even though it's counterintuitive, if you subtract, we move right. And if you add, we move left. Now for all of these actions we can take on a function to shift around the graph or to move it around, we can take multiple. So we could move a graph up and right and rotate it and stretch it if we wanted to. So now that we know what these actions do, let's look at some examples of how we can use these to figure out the way that graphs are changing.